Thanks for the invitation. My name is Tamy Boubekeur. I am the Director of Research for 3D and Immersive at Adobe. And I want to share a little bit about the way we use ray tracing in our product and our research. Okay, so let me start. First, in terms of context, Adobe is going 3D with stronger steps every day. We have strong foundation. We do have the Substance suite with us, which is the core technology that we are pushing these days, and we are preparing the next generation of 3D digital content creation tools for creatives. You might recognize this. This is a Substance Painter. This is one of our products. It's basically a Photoshop for 3D surfaces, where you can paint materials on objects and see at interactive rate the reflection of light on the surfaces. And I insist on that. Designing digital materials means designing an object that basically models how light reflects on the surface and how you perceive it. To that respect, physically based rendering is key. And of course, in this context, ray tracing is a technology on which we invest a lot. So I like to see rendering and ray tracing in particular as part of a larger picture, of a broader picture that involves like all the steps, models, algorithms, and implementation of computer graphics, from the shape model to the appearance model to the way you solve for visibility and to the way you implement it. Recently, we had hardware supported ray tracing, where you can now program your GPU with specific shaders to solve for ray tracing queries. And that changed quite a few things for us in terms of what we can achieve in real time and how we can leverage that for content creation. Now, of course, there are plenty of opportunities for ray tracing technologies in DCC, but what's important is that it's not only about rendering. So the ability to trace rays extremely fast on modern GPUs means that you can go beyond pure visualization. Of course, I talk a little bit about how we use that for rendering engines, but in terms of actually content creation and even machine learning, high performance ray tracing has a lot of impact on our workflows. I conclude this talk with a few notes about the current trends, one trend in particular, and challenges for future research. But let me start with the obvious, rendering. Of course, real-time ray tracing is mostly promoted for rendering purpose. This is a screen capture from one of our tools, Substance Designer, where people assemble complex digital materials based on a graph, a procedural graph made of nodes that synthesize the element of the final maps that are used and consumed by the rendering engine. What's important here is that when you adjust and design such materials, you are only interested in the final look of those materials. And what you need to do is basically to provide an extremely precise response for each pixel coming from the material and accounting for the environment lighting. So in this tool, for instance, we have a high performance ray tracer provided by NVIDIA called iRay that we use to fuel the user with the ability to switch between a highly interactive mode and almost real-time mode using path tracing. So we had that before actually the hardware support of ray tracing for GPUs, and now we are moving toward full support of it. Now, again, coming back on the fidelity question and how you need to make sure that while you are authoring your material, you are authoring something which at instant feedback gives you a response which is extremely close to what the final rendering will look like. Our recent iterations of a rendering have led us to provide ray tracing at all stages, from previs to a quality that is close to final frame. The picture you see here is a screen capture from the Star Wars, and over the last few years, the Star Wars movies and the teams at ILM have been using the Substance suite for modeling the materials. And of course, when you design those materials, you don't want to switch between a content creation tool and a final rendering tool to see if the content that you have been created is exactly what you want in the final picture. So having the ability to perform physically based path tracing in real time in the digital content creation tool is key for many of our users. Another of our tool, Adobe Dimension, is mostly designed for staging 3D shapes. And here again, when you want to promote the quality of the material or of the shapes of your asset, it's highly important to, in real time, have a feedback about how light interact with those materials. So during content authoring, real-time ray tracing provides fidelity, and for many applications, actually, the progressive nature of real-time path tracing is key. You get a solution that refines over time, and after a few seconds, you get an image that, at least in the asset scenario, is close to the final quality of the rendering in the final application. From an engineering perspective, it's somehow also easier and more sustainable to write shading codes for path tracing, mostly because it's really hardly funded on physics and less on a collection of hacks that we might know in real-time rendering based on rasterization. And like a side effect of having today's real-time rendering framework available to everyone is that they are scalable. And I will just show you an example. We are basically here doing some experiments with real-time path tracing on the GPU, and we use NVIDIA RTX for that. And this object is extracted from the Moana island scene. It's 37 million triangles. It's nothing new to see millions of triangles rendered in an interactive path tracer, actually, even before RTX and GPU supporting ray tracing that was possible. What's really interesting here is that it's coming out of the box, which means we didn't do anything special here to be able to render those millions of polygons at interactive rate with path tracing. The scalability needed to map path tracing and ray tracing onto the GPU actually brings that kind of side effect benefit, which is that it scales already. That was for the obvious. Ray tracing is, of course, a rendering technique, but ray tracing is also a mechanism that can help you measuring other things. And by measure, I mean really going over the surface of your assets and then extracting information that will be used for the content creation itself. In the Substance tool suite, we heavily use baking. So baking means basically taking a 3D shape and extracting parameters from it. Some are very simple, position of samples, normals, tangent planes. Some are more complex to evaluate, like ambient occlusion, curvature, thickness. And we leverage real-time ray tracing to actually compute those additional features on the 3D shape. Now, why doing that? It's because in the content creation pipeline, it can be highly informative to have some local notion of all those quantities when you actually design the 3D materials. And we leverage that for smart materials, materials that adapt to those properties that we measured through ray tracing. In this case, ray tracing is not a rendering mechanism. It's a measuring machine that helps us to fuel the programs that we call smart materials. It's an extremely powerful mechanism that the Substance users are using heavily. And there are several benefits to it. Of course, it helps sampling a variety of shape-related attributes, such as curvature, ambient occlusion, thickness, that can drive many processes during the content creation. But also, to some extent, it's shape representation agnostic, which means that although today triangles are the dominant breed of surface representation for content creation, on the long run, 5 years from now, if the shape representation change, if the first-class citizen is no more a triangle mesh, then all the work you might put into developing a ray tracing technology is actually preserved as long as the new shape representation provides an intersection primitive. And that's all you need to actually leverage out of that. Of course, with the Substance team, we use intensively those mechanisms for material editing, but the same principle could actually be used for animation or even modeling, going from core structure to mesostructure. Last, and that's probably the most important aspect of it, substances are procedural graphs that define the appearance of objects, and this procedural aspect plays along fairly nicely with those extra measured attributes. In practice, what happens is that a given 3D shape, which gives birth to a collection of those attributes that will themselves drive the procedural content creation. So somehow, a large part of this content creation is automated based on the shape itself. That's really the power of this mechanism. As an example of how we leverage real-time ray tracing, actually, Substance Designer and its bakers have been using the RTX technology from day one, and we already have 2 years of experience using this. Let me take now another example of how you can use high-performance ray tracing for content creation. And here I'm going to take the machine learning scenario. Let me first show you an example of a recent technology that we shipped a few days ago in the new Substance Alchemist release.
Tamy, are you able to explain? There is no audio, but perhaps you could explain.
Sorry, there is actually audio with the video, but I wasn't sure it was broadcasting. So what you see here is basically a technology that converts a single image to a physically based material. So what it does is that from a single photo, it's going to extract the albedo, normal map, roughness map, and everything that makes the parameters you need when you render a surface with a given material to evaluate light reflection. And what's impressive here is that the system accounts for the micro-detailed geometry to kind of remove the shadows that are present in the photo and get only the parameters of the underlying materials so that you can reuse them in new lighting conditions. And the example you see here is how out of 4 photos, we're creating 4 digital materials that were used in the 3D scene. So for many businesses and many application scenarios, this is really a big win. With just a smartphone, you get immediately digital content, digital materials to map your surfaces. I'm taking this example basically because it is based on learning from synthesis. So in learning from synthesis, what you do is that basically you synthesize the data you're learning from, taking millions of examples. And that's actually an important aspect of that, the ability to synthesize a lot of different variation of materials so that you train an AI to recognize them means that you need to be able to actually render them very fast because you need to render millions of them. We are in 2020, so probably that all the data sets that could be used for learning have been used for learning. And when you start to synthesize the data you want to learn from, you open up a lot what you can achieve in terms of data-driven processing. So what we do here is basically learning from synthetic data that we render at high performance. And in the new iteration of the technology, actually, we are using intensively real-time path tracing to do that. There are several benefits to it. Of course, first, we learn from data we never had to capture. We use procedural models to actually generate exemplar data in millions and then learn from them. But there is another benefit to it, which is that you can specialize the data sets as you wish you're learning from, which means that for some application-specific scenarios, you can decide that, for instance, all the materials that you will capture are of a certain breed, and you will synthesize the right set of data to learn from it. Of course, from a scientific perspective, you would like to have the as generic as possible AI to do that. But in practice, from an industrial perspective, this has a lot of benefit. We can make smaller learners and learn faster. Nowadays, the research is actually very active here, and actually Adobe research is working a lot on those topics. There are probably 2 big trends: end-to-end training with differential rendering, when you make the rendering mechanism itself differentiable and you can actually learn through the renderer. And from a more general perspective, neural rendering is actually taking off. I encourage you to look at this summer SIGGRAPH program to have a few sneak peek of the last evolution of this research topic. Let me conclude my short talk about the trends that I see still highly present in the real-time ray tracing field. The elephant in the room, of course, noise. When you do real-time path tracing, you do have a lot of noise. And actually, the problem of noise is common to offline path tracing, real-time path tracing. There are different strategies to address it, but in the end, the same fundamental problems appear. What you see here is an image that coming from a demo that we showed at SIGGRAPH 2018, and that was a denoising technology that we developed together with Ubisoft for a TV series called Raving Rabbits. The challenge there was to be able to actually denoise all those many renderings in a small amount of time, because actually the number of episodes in the TV series is really high, the number of images in total is really high, and you cannot afford spending minutes or hours denoising that kind of final output. I won't comment too much on the technical aspect of it. It's based on the Bayesian framework, but I'd like rather to comment on why denoising is so important in ray tracing. So here is an example of a 4 sample per pixel image. Here, basically, we trace 4 paths per pixel and average their response. If you trace 24 samples, the amount of noise is still highly perceivable and definitely a problem with this picture. And the problem is that even when you multiply by 10 this, you of course get still a lot of noise in the final picture. And I'm pretty sure that if you look closely to this image with 64,000 samples per pixels that took hours to render, you might actually still see a little bit of noise here and there. The framework we developed to actually address that back then, that was a research project from 2017, was based on a Bayesian model. So basically trying to learn how similar pixels may have a similar noise model and then a similar response, and trying to model this prior explicitly on a per patch basis to denoise the image collaboratively. No need to really look at all those little boxes. What's important here is that even if the method, which is by the way available on GitHub, it's open source, even if the method works well for production scenarios, it doesn't scale yet to real-time scenarios, and that's one key question. You can see here a 32 sample per pixel sequence, which is denoised with our method. It's an interesting case because somehow this is not the usual academic case. You do have transparent materials, you do have highly specular materials, and you still want to remove the noise from it. You cannot really look into the geometric properties of each pixels, the piece of geometry it covers, the tangent plane on the geometry it has. You cannot really rely on the features that you can measure in the scene. You have to only trust the radiance response that are measured with your path that you trace, and then do your magic there. You can see here a few examples of how the denoiser work. And really for the future, one thing we want to work on is starting from all this. This is an example actually of one of the many papers that have been published recently on denoising. There are many techniques, some based on neural nets, some based on other machine learning framework, but there is still a lot of research to do here because there is no perfect solution yet. And even more when it comes to the real-time scenario. One specific aspect we'll work on in the near future is how denoising for real-time path tracing can be specifically designed for the content creation case. It's actually quite a different scenario than VFX, animation, or games. During content creation, there are a set of specific events coming from the edit session of the user that you can account for to decide how to allocate the budget of samples we have for one frame to depict as much as possible how one action from the user influence the final result in the image. There is also limited dynamic. In professional scenarios, users are typically not changing everything in the scene at every frame. They just focus on some aspect of it, and that can help designing specific denoising methodologies for that. Finally, there has been a lot of work recently, in particular for the real-time case, to reuse samples over time. And we're thinking about how we can use basically a different space in which we're projecting samples previously measured, taking into account the edit that the user has been doing so far. So if I wrap up, we use in our product high performance ray tracing, not only for rendering and visualizing 3D objects or materials, but also to actually enrich the 3D data with additional measures that actually fuel the content creation pipeline and help designing more realistic materials and shapes. We found also that the speed at which you can synthesize images with that kind of technology helps a lot in the learning framework when you try to learn from data that you actually synthesized. I'd like to conclude with just maybe a reference for you all to have a look into. I've been trying to show here that in a few minutes that ray tracing can be useful to more than just rendering. It turns out that other researchers are also working on adapting that kind of framework to other problems. And this is a very interesting example. This is a work that will be presented at SIGGRAPH next summer. It's basically a Monte Carlo framework, so the root of modern path tracing. It's a Monte Carlo framework which is used to solve PDEs on 3D domains. So it's basically helping performing geometry processing without having to actually mesh the domain or build complex system of equations, just by mimicking a principle that is very close to Monte Carlo path tracing. I find it very interesting because geometry processing has even a much wider impact on visual computing than rendering, and starting to use basically ray-based techniques to solve that kind of problems means that actually real-time ray tracing can have impact way beyond the production of images. That's it for me. Thanks everyone. Enjoy the summit.